You live inside a miracle machine that lies to you every day. Your brain tells you the world is sized for your hands, your feet, your errands, your little wins and losses. But the universe does not care what feels intuitive. It runs on scales so big that your instincts break, and on distances so vast that even the word far starts to feel childish. Tonight we're going to stretch your sense of reality until it creaks, then keep going. Stay with me, because the payoff is worth it. And if you want more deep dives like this, like and subscribe. Start with the closest thing you can picture without effort. The room you are in right now, the distance from your chair to the door, the length of your arm, the width of a window. Everything about your daily life is built around these human-sized measurements, because they are the ones your nervous system evolved to handle. You are an animal that learned to survive by judging the leap between two rocks, the run to the next tree, the time until the sun dips below the horizon. Now here is the first trick. Your brain is good at feeling size, but only inside a tiny bubble. Past a certain point, it stops feeling and starts guessing. You can stand at one end of a long hallway and still feel the other end. You can look across a street and feel the distance. You can look up at a building and feel its height, but go bigger than that and something strange happens. The numbers keep increasing, but the feeling does not. So let's expand the bubble, step by step, and watch where the feeling snaps. Imagine you walk outside and decide to cross your neighborhood on foot. You know what that means. You know the rhythm. You know when your legs start to complain, when your breathing changes, when the world starts to feel bigger than your usual radius. You can do the same with a city. You can drive across it, measure it in traffic lights, turns and familiar landmarks. A country gets harder, but you still have anchors. You have time zones, flights, road trips, maps that fold like secrets. Then we arrive at the real problem, the moment the planet becomes the unit. Earth looks enormous because we live on it. It feels infinite because we never see it all at once. The ground does a very convincing job of pretending it is flat, and the sky does a very convincing job of pretending it is a ceiling. Even the ocean plays along. It goes to the horizon, then vanishes, as if reality simply runs out. Your brain loves horizons. Horizons are where predators might appear. Horizons are where food might be found. Horizons are where stories begin. But the horizon is a geometry trick. It is not the edge of Earth. It is just the limit of your line of sight on a curved surface. Here is a simple dare. Try to feel the size of Earth using only time. Earth's circumference is about 24,900 miles. Picture getting in a car and driving around the whole planet at a steady highway speed. No brakes, no sleep, no traffic, no borders, no oceans. Just distance, rolling under you like a conveyor belt. If you drove at about 70 miles per hour, it would take roughly 350 to 360 hours. That is about 15 days. 2 weeks of continuous motion just to trace the outline of the world you wake up on every morning. 2 weeks does not sound that crazy, right? That is the trap. 2 weeks feels like a long vacation. 2 weeks feels like a miserable stretch at work. 2 weeks feels like time you could spend becoming someone else. Your brain can still hold that. But Earth is not just a loop. Earth is a sphere. The planet is about 7,900 miles across. From one side through the center to the other, that is the diameter. And the surface area is about 197 million square miles. Those numbers are not meant to be memorized. They are meant to be felt as a warning. You're standing on a world so large that most of it will never touch your skin, never meet your eyes, never enter your personal story. You will live inside a tiny patch and still call it a lifetime. Now pause and notice something unsettling. Even with all those numbers, Earth still feels like home. It still feels like the main stage. That is not because it is large. It is because it is familiar. Familiarity is not the same thing as scale. Let's do another move. Imagine you could rise straight up from your house, like an elevator that ignores physics, passing over rooftops, then over neighborhoods, then over highways that shrink into thin threads. The rivers become handwriting. The coastlines become brushstrokes. Cities become glitter. The first time you see Earth from high enough, something emotional happens. The planet stops being a place you're inside and becomes an object you're looking at. It is the same Earth, but your relationship to it changes. Even at low orbit, the world is already starting to look like a map. The International Space Station, which is our most famous human outpost in space, circles Earth every roughly 90 minutes, moving at about 17,000 miles per hour. It is still close in cosmic terms, but emotionally it is a different universe. From there, you can watch sunrise and sunset multiple times in a single day. Your brain starts to realize that time and distance are not just numbers, they are perspectives. And here is the quiet punchline. Even the space station, even the edge of the atmosphere, even the line where the sky turns black, is still basically hugging Earth. You have not left the neighborhood. You have stepped onto the porch. This is where the story becomes dangerous because the next steps will not scale the way you expect. When we say Earth is big, we mean big relative to a person, big relative to a house, big relative to a city. But the universe does not grade on that curve. The universe grades on its own curve, and on that curve, Earth is a speck, a seed, a rounding error that happens to think. There is a reason your instincts are so bad at this. You did not evolve to understand planets. You evolved to understand paths through grass, and which noises in the dark mean trouble. So when you try to imagine global scale, your mind reaches for stories, not geometry. It imagines a long journey. It imagines a long fall. It imagines a long wait. It does not imagine a sphere with a circumference that could swallow your life in a loop of asphalt. So we're going to cheat. We're going to turn distance into time, and time into emotion, and emotion into understanding. Because if we cannot feel the size of our own planet, there is no chance we can feel what comes next. And that is the turn in tension for tonight. Earth is not the big thing in this story. Earth is the starting line. Earth is the warm room we will keep looking back at as everything else grows colder, darker, and more absurdly vast. Look up on a clear night, and the moon feels like a neighbour. It hangs there with a calm confidence, bright enough to cast shadows, detailed enough that you can pick out dark plains and pale highlands. Your eyes and your instincts whisper the same lie. That thing is close. If you had to, you could get there. But the moon is about 239,000 miles away. That number is already big enough to blur, so let's translate it into something your body understands. Imagine getting into a car and driving toward the moon the way you drive toward anything else. A steady highway speed, no traffic, no stops, just the road unrolling forever through the black. At about 70 miles per hour, it would take you roughly 5 months of non-stop driving to reach a place that looks close enough to touch from your backyard. 5 months. Your brain does a weird thing with that. It tries to shrink it. It thinks, I have waited 5 months for things, a season, a project, a relationship to change. And because time can be emotionally familiar, the distance tries to feel familiar too. But notice what just happened. We did not even leave Earth yet, and we're already using psychological tricks to keep from falling off the edge of comprehension. Now flip the story. In the 1960s, human beings did not drive to the moon. They punched through the air on columns of fire and then fell into orbit like thrown stones that refused to land. The Apollo missions moved through space at around 25,000 miles per hour. That is roughly 350 times faster than highway driving. At that speed, the trip took about 3 days. 3 days sounds like nothing. 3 days is a long weekend. 3 days is a business trip. 3 days is the amount of time it takes for a cold to turn into a cough and then move on. And that is exactly why the moon is such a perfect trap. It is far enough to be space. It is close enough to still fit inside a human calendar. So let's push on the feeling again, because the feeling is the thing we are trying to upgrade. Here is one of my favourite scale tricks. Shrink Earth down to the size of a tennis ball. Not a globe, not a beach ball, a tennis ball you could toss from hand to hand. Now place the moon at the same scale. How far away should it be? About 24 feet. That is the length of a typical living room. Not right next to you, but not across the city either. You could stand at one end and see the other end without effort. You could raise your voice and be heard. At this scale, Earth and Moon are a pair of objects in the same room, separated by a distance that feels casual. And now comes the detail that turns casual into eerie. At this scale, all the other planets would still be tiny, and the gap between Earth and Moon would still be so wide that you could line up the entire inner and outer planet line up between them. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. All of them, end to end, squeezed into the space between a tennis ball and its little companion across the room. That is the first moment when the moon stops being a friendly lamp in the sky and becomes a lesson. Space is not mostly stuff. Space is mostly distance. Now let's add the most human measurement of all. Conversation. When the astronauts walked on the moon and spoke back to mission control, there was a delay. Not a huge one. Not the kind of delay that makes you forget the question before the answer arrives, just enough to be noticeable. Just enough to feel wrong. It takes light a little more than a second to cross the distance between Earth and the moon. Radio signals travel at the speed of light, so every sentence had to make the trip. You can hear that delay in the recordings. It is subtle, but once you notice it, you cannot unhear it. A question goes out, a pause, an answer returns, and inside that pause is the real distance between worlds. That pause is doing something important. It is breaking a spell. On Earth, distance is a problem we solve with vehicles and roads and fuel. On the moon, distance becomes a physics fact that you cannot negotiate with. Even when you're talking to someone, even when you're connected by technology, you're still separated by a measurable gap in reality itself. And again, this is only the doorstep. We say the moon is far, but in cosmic terms it is practically touching us compared to the distances we're about to explore. The moon is still part of our immediate neighbourhood. It tugs our oceans, stabilises Earth's tilt, and quietly keeps our nights from being truly dark. It is a companion, a landmark, a gravitational partner in a slow dance that has been going on for billions of years. But the deeper message is the one hiding in plain sight. The moon teaches you that your eyes are not honest. It looks close, and it is not. It looks small, and it is not. It looks like a coin, and it is a world. It looks like it belongs to the sky, and it is a rock in space orbiting another rock in space. So here is the central question we're walking into now. If the moon can fool you this badly, what else have you been casually misunderstanding? Because once you accept the moon as distance, not decoration, you start to notice a pattern. You start to realise that every bright point above you is not a light on a ceiling. It is a location, a real place with a real separation from you, a place that creates delays, gaps, and silences that no amount of optimism can erase. That first little pause in the Apollo recordings is the beginning of a much larger silence, a silence that grows as we step away from Earth, away from the moon, away from the comforting idea that everything important is nearby. In the next step, we trade a distance you can still imagine for one that will start to feel like a magic trick. We leave the moon behind, and we aim our attention at the nearest furnace in space, the object that holds almost everything in our local story together. And once we do, the moon will feel like a memory you can hold in your hand. The moon teaches you distance with a gentle slap. The sun teaches you distance with a grin that says, you have no idea what you're standing next to. Because the sun is not just far, the sun is powerful far. The sun is far in a way that still reaches into your eyes, your skin, your weather, your food, your mood. It is a furnace so dominant that everything in our local space story is basically a footnote to it. On average, Earth sits about 93 million miles from the sun. That number is the first big bridge between human scale and solar system scale, and it is so large that we usually hide it behind a concept. We call it an astronomical unit, which is just a fancy way of saying The Earth to Sun distance is so useful as a ruler that we gave it a name, but let's not hide, let's feel it. Light from the Sun reaches Earth in about 8 minutes and 20 seconds. When you step outside at noon, the sunlight hitting your face left the Sun more than 8 minutes ago. If the Sun could somehow vanish in a puff of cosmic absurdity, you would keep seeing it for 8 minutes. You would keep feeling warmth for 8 minutes. The sky would keep pretending everything is normal for 8 minutes. Then it would all change at once. That is the first time distance becomes time in a way your instincts cannot ignore. The Sun is not a lamp. It is a star, and you're riding around it while seeing its past. Now here is where the story gets really strange. That 8-minute number feels big because it is the first time delay that you can actually notice. But it is also misleading because it makes the Sun feel like a simple point with a simple path between it and you. The Sun is not a point. It is a colossal sphere of plasma about 865,000 miles across. You could fit about 109 Earths side by side across its diameter, and the Sun contains about 99.8% of the mass in the entire solar system. Almost everything that exists here exists because the Sun is heavy enough to hold it. It does this with gravity, the quiet rule that never takes a day off. Inside the Sun, pressure becomes a kind of madness. The core reaches around 27 million degrees. Under that pressure and heat, hydrogen nuclei are forced together. Fusion happens, mass becomes energy. Energy becomes light. Light becomes heat. Heat becomes the reason oceans stay liquid instead of turning into permanent ice. That is the tidy version we learn in school. But the real version has a twist that deserves a drum roll. The light that hits your face did not leave the core 8 minutes ago. It may have been born 10,000 years ago, 100,000 years ago, possibly longer. Here is why. Inside the Sun, light does not stream out in a straight line like a beam from a flashlight. The Sun is dense. Photons, the particles of light, are constantly being absorbed and re-emitted, scattered and bumped, turned around, shoved sideways. They take a random walk, a drunken, staggering path through a thick, glowing crowd. So even though the Sun is less than 1 million miles across, and even though light moves incredibly fast, it can take thousands to hundreds of thousands of years for energy created in the core to finally escape the surface as a photon that can fly freely through space. So when you feel sunlight, you are literally touching ancient energy. Not ancient in the sense of dinosaurs, ancient in the sense of human civilization. Some of that light may have started its journey outward before the first cities existed, before written language, before anyone on Earth had the slightest clue that a nuclear furnace was humming above them. Distance just became time in a second way, not the travel time through space, the escape time from a star. And now, with that in mind, the inner solar system looks different. Mercury is the closest planet to the Sun. It is a world of extremes because it is small, airless, and exposed. Its days are long, its nights are long, and without a thick atmosphere to move heat around, the surface can roast and then freeze. Mercury is also a reminder that closeness has consequences. The Sun's gravity grips harder here. The speed of everything increases. Venus is next, and it is the most brutal plot twist in the inner solar system. If you only knew its size, you might call it Earth's twin. Nearly the same diameter, similar mass, similar composition. But Venus is a warning story about atmospheres. It is wrapped in thick clouds and dense air loaded with carbon dioxide, trapping heat until the surface becomes an oven. Pressures at the surface are crushing. Temperatures are hot enough to melt lead. Venus is what happens when a planet keeps the Sun's energy and refuses to let it go. Then comes Earth, the improbable sweet spot. Not too close, not too far. With liquid water, a breathable atmosphere, plate tectonics, and a biosphere that has been rewriting the surface for billions of years. Earth is not the default. Earth is the exception that got lucky and then got weird, and then Mars. Mars is the planet we keep staring at because it feels like the next chapter. It is colder, smaller, drier, with a thinner atmosphere, yet it carries the scars of a wetter past. There are valleys and channels that look like ancient riverbeds. There are minerals that form in water. There are ice caps and underground ice. Mars is a place that might have been hospitable once, and might be again with enough engineering and time, but right now, Mars is also another lesson in delay. When we send signals to a rover on Mars, the message does not arrive instantly. Depending on where Mars and Earth are in their orbits, the one-way light travel time can range from a few minutes to more than 20 minutes. That means a command from Earth is not driving a robot like a remote control car. It is sending instructions into the future. It is talking to a machine that is already living in the next part of the story, waiting for your words to catch up. This is where the tension shifts again. The Moon gave us a pause of a little more than a second. Mars gives us pauses you can feel in your chest, long enough to make you anxious. Long enough to make you realise how fragile control really is. When the delay grows, you cannot steer in real time. You must predict. You must trust. You must accept that your influence has become slow, and we are still in the inner solar system. The sun's light rules all of this. The orbits, the climates, the chance of life, the way we explore, the very meaning of near and far. It is the beating heart that powers the local neighbourhood, and it is also the first major object that forces you to confront the true emptiness between things. Because the inner planets are not sitting next to each other like beads on a string. They are separated by huge gulfs of nothing. Space between them is not just a gap. It is a vast arena where you could lose entire worlds and still have plenty of room left over. So when people say, "We will go to Mars," remember what that really means. It means we will throw a small, fragile bundle of life across tens of millions of miles of vacuum and radiation, following a curve through space with no road, no rescue, no shortcuts, just physics. And this is still just the warm part of the story, the place where sunlight is strong and the distances can be measured in minutes. In the next part, we step beyond the inner planets into the realm where gravity builds something that looks like a solar system inside the solar system. A kingdom of moons, storms, and magnetic violence that makes Earth look like a quiet pebble. Jupiter is where the solar system starts acting like a different genre. Up close, the inner planets feel like a family drama. Small worlds, thin skins of air, fragile balances. Then you go outward, and suddenly you're staring at a king planet that could have been a star if it were just a little more massive. Jupiter is not merely another stop on the map. It is a gravitational regime, a place where the rules feel louder. On average, Jupiter orbits about 484 million miles from the Sun. That is far enough that sunlight is weaker, colder, more distant. But Jupiter does not need warmth to feel alive. It carries its own violence. It radiates more heat than it receives, slowly bleeding energy left over from its formation, and that extra internal heat feeds the motion you see in its clouds. Even through a telescope, Jupiter looks like a living object. Bands of colour, swirls, bright ovals, dark belts, storms that seem to stare back. The most famous is the Great Red Spot, a storm larger than Earth that has been raging for centuries. It has changed shape over time, shrinking compared to old measurements, but it remains a symbol of what happens when a planet has no solid ground to interrupt the wind. Those winds can race at around 400 miles per hour, and because Jupiter is mostly hydrogen and helium, more like a failed star than a rocky world, there is no surface the way you're used to. If you tried to descend into Jupiter, you would sink through thickening gas, then thicker and hotter layers, until the pressure becomes crushing. The deeper you go, the more Jupiter stops being a place and becomes a physics problem. Gravity is the first reason Jupiter feels like a kingdom. It is so massive that it dominates the outer solar system, pulling and nudging smaller bodies, reshaping orbits, acting like a bouncer at the door of the Sun's larger neighbourhood. It also has a magnetic field that is roughly 20,000 times stronger than Earth's. That field creates an enormous magnetosphere, a bubble of magnetic influence that deflects charged particles from the solar wind and traps others in belts of radiation. This matters because it changes what space feels like near Jupiter. It is not empty calm, it is charged and crackling. It is full of invisible hazards that can fry electronics and punish anything careless enough to linger. So here is the central question for this part. If Jupiter is this intense as a planet, what does it do to the worlds that orbit it? The answer is one of the best reveals in the solar system. Jupiter is surrounded by moons the way a small star might be surrounded by planets, not a few rocks. An entire system. Dozens of moons. Many of them big enough to be planets if they orbited the Sun instead. And among them are 4 that change the way humans think about the universe. In the early 1700s, Galileo Galilei pointed a telescope at Jupiter and noticed something shocking. Tiny lights near the planet that moved from night to night. They were not stars, they were moons, worlds in orbit around something other than Earth. That single observation helped dismantle the comforting idea that everything revolves around us. Those 4 moons are still the stars of Jupiter's show. Io, Europa, Ganymede, Callisto. Each one is a different answer to the question of what a world can be. Io is the wildest. From far away you might expect an icy moon, cold, still, quiet. Instead, Io is the most volcanically active world we know. Its surface is constantly being resurfaced by eruptions, painting the landscape with sulphurous colours, yellows, reds, blacks. It looks like a world that cannot sit still. Why? Because Jupiter and the other moons pull on it. Io is trapped in a gravitational tug-of-war. As it orbits Jupiter, the planet's immense gravity stretches and squeezes it, not once, but constantly. This flexing generates heat inside Io, like bending a paperclip back and forth until it gets hot. The result is tidal heating, a process that turns an otherwise cold moon into a volcanic furnace. When you realise this, you start seeing the solar system differently. Distance from the Sun is not the only source of energy. Gravity can be a power plant. Europa is the opposite kind of shock. Europa looks smooth and bright, a shell of ice etched with cracks and streaks, like a frozen eye. For a long time it was easy to dismiss it as just another icy moon. Then the data started whispering something else. Beneath that ice, Europa almost certainly hides an ocean of liquid water, warmed not by sunlight, but by tidal heating, stirred by flexing, kept alive by Jupiter's pull. Some estimates suggest Europa's ice shell might be 10 to 15 miles thick in places, though the exact thickness is still debated. Under that, an ocean potentially deeper than all of Earth's oceans combined. Water. Heat, chemistry. These are 3 ingredients we keep circling whenever we talk about life. Europa does not promise life. It does not guarantee it. But it turns life from a fantasy into a serious question. If an ocean can exist in the dark, under ice, far from the sun, then the universe might be more habitable than we ever expected. Now the story shifts again, because Jupiter's largest moon is even bigger than the planet Mercury. Ganymede is enormous, the largest moon in the solar system, and it does something no other moon does. It generates its own magnetic field. That means it has an internal dynamo, motion inside that creates magnetism, hinting at a complex interior. It likely also hides a subsurface ocean, perhaps layered like a strange cosmic parfait, with different phases of ice and water under extreme pressure. Ganymede feels like a world that wanted to be a planet and almost succeeded. It has grooves and ridges across its surface, evidence of tectonic-style deformation long ago. It is a moon with its own space weather, its own magnetic environment, nested inside Jupiter's larger magnetic kingdom. Callisto is the last of the 4, and it carries a different message. Callisto is heavily cratered, ancient and quiet on the surface. It looks like a museum of impacts, preserved for billions of years because it has not been resurfaced the way Io has. If Io is a living furnace and Europa is a hidden ocean, Callisto is a memory, a record of early solar system chaos when collisions were common and nothing was safe. And yet even Callisto may hide an ocean beneath its battered crust, suggesting that water might be a recurring theme out here, not a rare miracle. So what is the dramatic turn? It is this. You came to Jupiter expecting one big planet. You found a whole system. You found worlds with volcanoes, worlds with oceans, worlds with magnetic fields, worlds that keep their histories like scars. You found environments where life could be possible in places we once would have called dead by definition. And here is the strange emotional effect. Jupiter makes Earth feel smaller, not just in size, but in imagination. Earth is no longer the obvious centerpiece. It is one example among many possible worlds, and some of those worlds might be far stranger and more promising than we ever guessed. But there is also a darker note. Jupiter's radiation belts make parts of this kingdom harsh and dangerous. Getting close to Europa, the place we most want to explore for life, means flying through an environment that can shred electronics and complicate every mission. Jupiter offers wonders, but it does not give them away for free. We are learning to explore these moons with patience and cleverness. We send orbiters, we plan flybys. We study magnetic signatures and gravity signals and the subtle ways a moon tugs back. We are building the skills to do archaeology on invisible oceans. And once you see Jupiter this way, the rest of the solar system starts to change shape. Because Jupiter is not unique. It is the first giant we meet, not the last. Beyond it are other worlds with rings like impossible jewelry, moons with thick atmospheres, and oceans that erupt into space. So now we leave Jupiter's stormlit kingdom behind, and we head toward the planet that looks like it was designed to make humans fall in love at first sight. Saturn is the planet that seduces you into forgetting what you're looking at. Those rings do not just decorate it, they rewrite it. They make a ball of gas look like a cosmic symbol, something too perfect to be real, like the universe decided to draw a logo. But Saturn is not an image. Saturn is a world, a giant one. It orbits roughly 890 million miles from the Sun on average, almost twice Jupiter's distance. Out here, sunlight is weaker, colder, and slower to warm anything. Yet Saturn still has its own weather, its own magnetosphere, its own strange moons that keep stealing the spotlight. The rings are the first obsession, so let's deal with them honestly. Saturn's rings are vast. They stretch hundreds of thousands of miles across, far wider than the planet itself, but their greatest trick is thickness. For all their grandeur, much of the ring system is surprisingly thin, often on the scale of tens of feet. That means something you can see from Earth as a glowing band is, in many places, thinner than a tall building. So what are you seeing? You're seeing an enormous flat swarm of countless particles, from tiny grains to chunks as large as a house, all orbiting Saturn like a disk of shattered ice. Their reflectivity and structure create the bright and dark bands that look so clean from a distance. The rings are a reminder that nature can build something delicate on a colossal scale. Then we meet Saturn's moons, and the story shifts from beauty to possibility. Titan is the showstopper. It is the second largest moon in the solar system, and it has a thick atmosphere. An atmosphere so dense that if you stood on Titan, the sky would be a hazy orange dome, and the world would feel strangely familiar in pressure, yet utterly alien in chemistry. Titan is cold enough that water is ice as hard as rock, but it has rivers and lakes and seas anyway, made not of water but of liquid methane and ethane. It has weather, clouds, rain, erosion, a whole system of cycles that mirrors Earth's hydrological cycle, only with different liquids. It is like watching a parallel version of planetary science, where the roles have been recast. Titan also likely hides something under the surface, another theme we keep running into. Evidence suggests a subsurface ocean of water mixed with other compounds beneath its icy shell, which means Titan might have multiple layers of habitability, a cold surface with alien weather, and a hidden ocean where chemistry could do interesting things in the dark. Enceladus is smaller, but it hits harder. Enceladus is an icy moon with cracks near its south pole that spray plumes of water vapor and ice into space. These plumes feed Saturn's E-ring and reveal something profound. There is liquid water inside, there is heat. There are molecules that hint at chemical energy sources. This is not just a frozen rock, it is an active system. And when a moon is literally venting material from an ocean into space, it means you do not have to drill through miles of ice to sample what is down there. You can fly through the plume, you can taste the spray, you can do ocean science without ever landing. That is why Enceladus is one of the most exciting places in the solar system for the search for life. Not because life is guaranteed, but because the ingredients are lined up in a way we cannot ignore. Now, while all of this is unfolding, something else is happening. Something you can feel if you keep your mind on distance. We are now far enough that communication itself becomes a different experience. A signal travelling at the speed of light takes about an hour and 20 minutes to travel one way from the Sun to Saturn, and Earth is in roughly the same neighbourhood of distance from the Sun. That means when we talk to a spacecraft near Saturn, we are not talking. We are sending a message into the future and waiting for a ghost of a reply from the past. This is where control turns into planning. When the delay is this long, you cannot joystick a spacecraft. You cannot react quickly. You must anticipate. You must design sequences. You must trust that your machine will execute the plan while you sit on Earth waiting in the slow silence between question and answer. And as we go farther outward, the silence grows. Uranus is next. Uranus orbits about 1,800,000,000 miles from the Sun on average. It is an ice giant different from Jupiter and Saturn in composition, with more water, ammonia and methane in its deeper layers. But Uranus is famous for one dramatic feature that makes it feel like a prank. It is tilted on its side. Its axis of rotation is tipped by about 98 degrees. That means Uranus spins like a rolling ball rather than a spinning top. Seasonal extremes become surreal. One pole can face the Sun for decades, while the other sinks into darkness. Then they trade places. This tilt likely came from a colossal collision long ago, a reminder that the solar system was once a violent arena, not a neatly organised family portrait. Uranus also has rings, faint and dark, and moons with strange terrains. Yet Uranus remains oddly mysterious because we have only visited it once up close with a spacecraft. That single flyby, the Voyager 2 encounter in the 1980s, gave us a glimpse and then left us with decades of questions. Then comes Neptune, the far blue world, orbiting around 2,800,000,000 miles from the Sun on average. Neptune is another ice giant, and it should be cold and slow and sleepy. But Neptune is restless. Its winds can roar at astonishing speeds, often sighted around 1,200 miles per hour in the upper atmosphere. It has storms too. The most famous was the Great Dark Spot spotted by Voyager 2, a storm system that later seemed to change and possibly vanish, reminding us that weather is not a permanent landmark even on planets. Neptune's largest moon, Triton, is also a twist. Triton orbits backward compared to Neptune's rotation, suggesting it was captured, not born there. Its surface is icy, but it shows signs of activity, and it might hold a subsurface ocean as well. Another hidden sea, another possible habitat, another layer of the universe that refuses to stay simple. Now step back and feel what we have done. We have moved from Jupiter's kingdom to Saturn's jewelry and hidden oceans, to Uranus lying on its side, to Neptune whipping winds in deep cold. And each step outward has stretched the silence. The communication delay grows, the sunlight weakens, the sense of control slips. This is the point in the journey where exploration becomes an act of faith in mathematics. When Voyager 2 flew past these worlds, it did not have a live pilot making quick decisions. It had instructions, trajectories, timing, and the relentless reliability of physics. The spacecraft was a message from Earth, flung outward, carrying our curiosity and our engineering, and it kept going even when the people who launched it got older, changed jobs, or died. That is a weird kind of intimacy. A machine travelling through the outer solar system is still connected to us, but the connection is stretched thin by distance and time. It is like calling across a canyon so wide that you hear your own echo before you hear your friend. And the most important shift is this. Even out here, among the giants, we are still inside the sun's domain. We are still within the region where sunlight matters and the planets orbit in familiar paths. We are still in the part of the story that feels like a system, a set of objects bound together in a shared dance. But the system does not end with Neptune, it fades. It dissolves into a frontier of smaller bodies, icy debris, and distant comets that form the boundary between our comfortable neighbourhood and the true void between stars. In the next part, we cross that boundary. We meet Pluto, we step into the Kuiper Belt, and we aim our attention at the farthest reach of the sun's gravitational influence, the place where the solar system ends not with a wall, but with a thin mist of ancient ice. The outer planets feel like a widening spiral. Each one is farther, colder, slower to answer, but at least they are still planets, still big enough to feel like destinations. Then you pass Neptune, and the map starts to change character. The solar system does not end with a final gate. It frays, it thins, it becomes a field of leftovers, icy fragments, dwarf worlds, and comets waiting in the dark like old thoughts you forgot you had. Pluto sits right on the edge of that psychological shift. For most of the 20th century, Pluto was the 9th planet, a tiny icon at the end of every classroom poster. Then in 2006 it was reclassified as a dwarf planet, not because it became less interesting, but because we realised it was not alone. We had discovered other bodies in the same distant region, some comparable in size, and the old definition of planet could not survive the new reality. Pluto did not shrink. Our understanding grew. Pluto is about 1,400 miles across, smaller than Earth's moon, and it orbits far enough from the sun that sunlight there feels like a distant spotlight, weak and pale. Its average distance is around 3,600,000,000 miles from the sun, though its orbit is elliptical so it swings closer and farther over time. Out there, the sun is no longer a blazing disk, it is a painfully bright star. And yet Pluto is not a dead rock. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a world with personality. Mountains of water ice, smooth plains that look geologically young, a heart-shaped region of nitrogen ice that became instantly famous, a thin atmosphere that expands and contracts as Pluto moves along its orbit, a moon system with Charon so large relative to Pluto that the pair almost feel like a double world. The most emotional part of that flyby is not what we saw. It is how long it took to get there. New Horizons launched in 2006 and arrived about 9.5 years later. It crossed billions of miles, moving at extraordinary speed, and still needed almost a decade just to reach this small distant world. The signal time delay alone is a mood. At Pluto's distance, light takes more than 4.5 hours to travel one way. That means every photo you receive from a spacecraft near Pluto is already old the moment you see it. Every command you send is a promise delivered hours later, and here is the twist. Pluto is still part of the inner story compared to what comes next, because Pluto is not the end. Pluto is a sign that you have entered the Kuiper Belt. The Kuiper Belt is a region beyond Neptune filled with icy bodies. Think of it as a distant ring of debris left over from the formation of the solar system, populated by dwarf planets, comet-like objects, and chunks of frozen material that have been orbiting quietly for billions of years. Pluto's a celebrity of this region, but it has company. Many objects out there travel in the same broad neighbourhood, each one a clue to the early solar system, preserved like fossils in deep freeze. The Kuiper Belt changes your sense of what the solar system is. It is not just a set of planets, it is a gradient, a transition from big worlds to countless small ones. Beyond the Kuiper Belt, the solar system becomes even more ghostly. There is another region we think exists, not because we have seen it directly in detail, but because comets tell us it must be there. This is the Oort cloud. The Oort cloud is imagined as a vast, roughly spherical halo of icy bodies surrounding the solar system at extreme distances. It might begin around 2,000 astronomical units from the Sun and extend outward to perhaps 100,000 astronomical units. And remember, 1 astronomical unit is the Earth to Sun distance. So we're talking about a boundary that could be thousands to tens of thousands of times farther away than Earth's orbit. This is where words like far start to break. The Oort cloud is not a tidy ring. It is more like a thin mist of ancient ice, loosely bound by the Sun's gravity. These objects are so distant that a small gravitational nudge from a passing star, or the slow tidal pull from the Milky Way itself, can disturb them. Some get knocked inward. They fall toward the Sun, brightening as they heat up, becoming the long-period comets that visit the inner solar system like strangers from a forgotten suburb. In other words, the Oort cloud is a reservoir of comets, a deep storage of icy bodies waiting for gravity to roll the dice. Now let's bring back Voyager, because Voyager is the perfect emotional yardstick here. The Voyager spacecraft were launched in the 1970s. Decades later, they are still travelling, still sending back faint signals, still carrying that famous golden record like a message in a bottle. They have passed the major planets. They have entered interstellar space, crossing the boundary where the solar wind gives way to the interstellar medium. And yet, even Voyager's 50-year journey is barely a step into the Sun's true gravitational neighbourhood, if the Oort cloud extends as far as we think. This is the most important tension shift in this part. We like to imagine we have gone far. We like to imagine that a spacecraft leaving the planets has escaped the solar system. But the solar system is not just where the planets are. The solar system is the full reach of the Sun's influence, and that influence stretches out into distances that make our greatest voyages feel like the first few steps of a walk. So here is the question that hangs in the air now. If the solar system can be this large, this diffuse, this stretched, then what does it mean to go to another star? What does it mean to leave the Sun behind for real? Because beyond the Oort cloud, the Sun's gravity finally loses its grip, and beyond that point, there is no more neighbourhood. There is only the true gap between stars, a darkness so wide that even the fastest thing in the universe takes years just to cross it. In the next part, we face that gap head on. We aim at the closest star, Proxima Centauri, and we let the number that sounds small, just over 4 light years, reveal itself as one of the most brutal distances a human mind can ever try to hold. Voyager has been racing outward for decades, moving at over 38,000 miles per hour, a tiny metal survivor of the 1970s that refuses to stop. After nearly 50 years of continuous flight, it has covered roughly 15 billion miles. That sounds enormous until you compare it to what comes next, because even a journey like that is still basically inside our solar system's backyard compared to the distance to the nearest star. The nearest star beyond the Sun is Proxima Centauri, a small red dwarf in the Alpha Centauri system. It is our closest stellar neighbour, the nearest sun beyond our own, and yet the distance is so large that miles start to feel like the wrong language. It is the kind of number that your brain tries to file under far and move on, because what else can it do? This is why astronomers use a different unit out here, one that turns distance into a story your mind can almost hold. A light year. A light year is the distance light travels in 1 year. Light is the fastest thing we know, and even for light, the distance between stars is not a quick hop. Proxima Centauri is about 4.25 light years away. That sounds manageable, almost cute. 4 years. People spend longer than that in high school. People spend longer than that recovering from heartbreak. 4 years feels like something a determined civilization could power through. But remember what that number really means. If you look at Proxima Centauri tonight, you are not seeing it as it is right now. You are seeing it as it was more than 4 years ago. If you're watching this in the year 2025, you are seeing it as it was in the year 2021. Whatever is happening there at this moment, whatever storms are raging, whatever flares are blasting off its surface, whatever quiet changes are unfolding, you are blind to it until the light arrives. The present moment is an illusion across interstellar distance. That is the first true abyss. Not just the emptiness, but the delay. The universe does not let you have instant knowledge. It rations reality. It hands you information only after time has passed, and the bigger the distance, the older the truth you receive. Now let's make it hurt in a way your instincts can feel. Imagine we built the fastest ship we could, and then we made it even faster. Take the Parker Solar Probe, a spacecraft built to dive toward the sun and survive. At its peak speed, it can reach about 430,000 miles per hour. That is a number that sounds like science fiction, like a bullet that never slows down. Even at that speed, the trip to Proxima Centauri would take thousands of years. You could launch your mission when the first pyramids were being built, and you still would not have arrived yet. You would still be travelling, still coasting through the emptiness, still waiting for a destination that never seems to get closer in any meaningful way. Now do the moon trick again, because your brain needs anchors. The moon is about 239,000 miles away. Proxima Centauri is so far that you could fit about 105 million moon distances between us and that star. That is not a poetic exaggeration. That is the scale shift. The moon, which felt like a different world, becomes a single step in a ladder that stretches beyond imagination. Another comparison lands even harder because it uses your body and your patience. A standard running track lap is a quarter mile. If you laid out 105 million quarter-mile laps in a straight line, and then you started running, you would be running through generations. You would be running through history. You would be running through the rise and fall of empires. You would not be running toward a star. You would be running toward the concept of a star. And this is where Voyager returns to the story, not as a hero, but as a reality check. Voyager has travelled for nearly 50 years, and it is still only a tiny fraction of the way to Proxima Centauri. The number is humiliating. About 0.025% of the distance, not 2.5%, not a quarter, 0.025%. That is what human progress looks like when you measure it against interstellar space. This is the point where most people get discouraged, or they get sarcastic, or they retreat into fantasy. So let's do something smarter. Let's treat this distance not as an insult, but as a discovery. Because the space between stars is not empty in the casual way you mean empty. It is empty in an almost philosophical way. It is a desert so wide that even the fastest traveller in the universe needs years to cross it. It is a silence so deep that even if civilizations exist out there, they may be locked into their own islands of time. And yet Proxima Centauri is not just a distant dot. It is a real star with real properties. It is a red dwarf, smaller and dimmer than the Sun, part of a system where two brighter stars, Alpha Centauri A and Alpha Centauri B, orbit each other every about 79 years. To the naked eye, those two bright stars can look like one point of light in the southern sky. Proxima is the quieter companion, much closer to us than the others, and much harder to see without help. Proxima also has at least one famous planet. Proxima Centauri B is an exoplanet orbiting in the star's habitable zone, the region where temperatures might allow liquid water on the surface under the right conditions. it is only slightly more massive than Earth. That phrase sounds like a promise, and it is tempting to imagine oceans, clouds, and continents under a red sun. But even here, distance teaches humility. Habitable zone does not mean habitable, it means potentially. Proxima is a red dwarf, and red dwarfs can be active. They can flare. They can blast planets with radiation. They can strip atmospheres or batter them into strange new chemistries. And because the planet is close to its star, it may be tidally locked, with one side facing the star all the time and the other side living in permanent night. A world like that could still be fascinating, still potentially life-friendly in some regions, but it would not be a second Earth. It would be its own kind of place. So here is the real question, the one that makes this part more than a number game. What does it mean to live in a universe where the distance to your nearest neighbour is measured in years even at the speed of light? It means relationships have horizons. It means causality has a lag. It means even if you could send a message to another civilization, the conversation would be slow, stretched across years, maybe decades, maybe centuries. It means the universe allows connection, but it does not make it easy. And that changes how you look at the night sky. Those points of light are not decorations. They are locations separated by gulfs of time. When you look up, you are looking into the past. Not in a mystical way, in a literal way. You're watching ancient light arrive, carrying stories from places you cannot touch and events you cannot witness in real time. This is where the scale shift becomes permanent. The solar system was a neighborhood. The stars are an ocean. And now that we have stepped into that ocean, the next thing we need to understand is what those distant suns actually are, how they live, how they die, and why their deaths seed the universe with the ingredients for worlds like ours. So let's talk about what those distant suns actually are. Not as points of light, not as decorations, but as machines. Stars are giant balls of gas, mostly hydrogen and helium, held together by gravity and powered by nuclear fusion in their cores. At a star's centre, the pressure becomes so intense that hydrogen atoms are forced together to form helium, and in the process, an ocean of energy is released. That energy fights its way outward and finally escapes as light and heat. The amazing part is not that stars shine. The amazing part is how long they keep going. And the reason some last almost forever while others die violently comes down to one ruthless variable: mass. The most common stars in our galaxy are red dwarfs. About 70% of all stars in the Milky Way are red dwarfs, but they are so dim that none are visible to the naked eye from Earth. Proxima Centauri is a red dwarf. Barnard's star is a red dwarf. These are the quiet workhorses of the galaxy, small, cool, and stubbornly long-lived. A typical red dwarf can be less than half the mass of our Sun, and some can be as small as about 8% of the Sun's mass. Below that limit, there is not enough pressure in the core to sustain hydrogen fusion. You do not get a star. You get a brown dwarf instead, a failed star that glows faintly from leftover heat, but never truly becomes a stable fusion furnace. Red dwarfs burn their fuel slowly, almost miserly. That is why they can shine for trillions of years. Our Sun will exhaust its hydrogen in about 5 billion years, but red dwarfs will still be shining long after the last sun-like star has faded. Our Sun belongs to a middle class of stars sometimes described as a yellow dwarf. From an astronomical perspective, it is not a celebrity. It is not especially hot, not especially cool, not especially massive, not especially tiny. It is ordinary in the best possible way. Best. Ordinary is exactly what a biosphere needs. Then you go up the mass ladder and the universe starts getting dramatic. Massive stars can be dozens or even hundreds of times the mass of the Sun, with surface temperatures around 50,000 degrees Fahrenheit or more. These stars live fast and die young. While red dwarfs sip their fuel over unimaginable timescales, The biggest stars burn like a bonfire in a windstorm. They shine brighter, they run hotter, and they tear through their nuclear fuel in only a few million years. That contrast should make you uneasy in a useful way. The galaxy is full of long-lived quiet stars, but some of the brightest beacons you see in the sky are the short-lived ones, the cosmic overachievers that are destined for spectacular endings. Betelgeuse is one of the most famous examples. It is the bright red star in the constellation Orion, a red supergiant near the end of its life. Betelgeuse is about 700 times the diameter of the Sun. If you placed Betelgeuse at the centre of our solar system, it would engulf the orbits of Mercury, Venus, Earth and Mars and extend past the asteroid belt. Just let that sit in your mind for a second. A single star swelling so large that it would swallow the inner planets like dust. Betelgeuse will explode as a supernova sometime in the next 100,000 years. That might sound like a long time, and in human terms it is. In stellar terms it is a blink. When it happens, it will be visible from Earth during the day, a star dying so violently that it temporarily competes with the Sun in brightness. Not because it moved closer, not because anything is chasing us, but because nature decided to end one life with a flash that can be seen across hundreds of light years. And this is where the story turns from awe to consequence. Because when massive stars die, they do not just disappear. They leave behind remnants that are, in their own way, even stranger than the stars that created them. If a star like the Sun exhausts its fuel, it does not explode in the same way as the biggest stars. It sheds its outer layers and leaves behind a dense core called a white dwarf. A white dwarf is roughly the size of Earth, but can hold a large fraction of the Sun's mass, packed into a volume so small that the matter becomes intensely compressed. One of the most famous white dwarfs is Sirius B, the companion to Sirius A in the Sirius binary system. Sirius A is the bright star you see. Sirius B is the collapsed remnant, about the size of Earth yet with nearly the mass of the Sun. The compression is so extreme that a teaspoon of white dwarf material would weigh several tons on Earth. A spoonful that would punch through the ground like a meteor. Now step up in violence. Neutron stars are the collapsed cores of stars that were between about 8 and 25 times the mass of the Sun. When these stars die, their cores collapse so violently that protons and electrons are squeezed together to form neutrons. The result is a neutron star that might be only about 12 miles across but can contain more mass than our Sun does. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. That number is not meant to be comfortable. It is meant to be a warning that the universe can build states of matter that do not exist naturally anywhere on Earth. Neutron stars are like atomic nuclei scaled up to the size of a city, gravity crushing matter into a form so dense that your imagination has to tap out. And then there is the final category, the one that makes even neutron stars feel almost normal. Black holes form from the deaths of the most massive stars, those more than about 25 times the mass of the Sun. When these giants collapse, nothing can stop the infell. The matter is crushed down beyond anything we can directly visualize, into a region surrounded by an event horizon, a boundary from which nothing can escape, not even light. Black holes are invisible by definition, but we can detect them by their effects on nearby matter and light. They reveal themselves through motion, through heat, through the way gas spirals in and glows before vanishing. A black hole is a place where the universe hides a piece of itself behind a one-way curtain, and still leaves clues outside for curious minds to follow. So here is the emotional punchline of this part. Stars are not just lights in the sky. They are factories and furnaces. They are timekeepers. They are the reason atoms heavier than hydrogen exist in abundance. They forge elements in their cores, then scatter them through space when they die. And those scattered elements become the raw material for new stars, new planets, and eventually, in at least one case we know, new minds that look up and ask questions. But to feel what that really means, we need to scale up again. One star is a story. A galaxy is a library of them. Hundreds of billions of stellar lives playing out at once, weaving patterns of light and dust across a structure so large that even the concept of home starts to wobble. So now we widen the lens and we step into the Milky Way itself. The night sky looks like it is happening now, but it is not. Every point of light you see is delayed reality, arriving late, sometimes by minutes, sometimes by years, sometimes by thousands of years. The sky is not a window into the present. It is a museum of old photons, each one carrying a story from a time you never lived in. Take the Orion Nebula, one of the most famous clouds in the night sky. It sits about 1,344 light-years away. That means the light you see from it began its journey when human history was in a completely different chapter. When you look at that nebula, you're seeing a version of it from roughly 1,344 years ago, a time when empires rose and fell without anyone knowing what a nebula even was. Inside that glowing cloud, gravity is doing the slow work of creation. Gas and dust collapse into denser knots, heating up, gathering mass, until newborn stars ignite and begin to shine. Some of the stars in that region are extremely young by cosmic standards, only a few 100,000 years old. Compared to our Sun, which is about 4.5 billion years old, those stars are practically still blinking awake, now moved from birth to death. The Crab Nebula is the aftermath of a stellar explosion that humans actually recorded. In the year 1054, astronomers in China wrote about a guest star that appeared in the sky. It was bright enough to be seen in daylight for a while, then it faded, leaving behind a glowing remnant we now call the Crab Nebula. But the mind-bending part is the timing. The explosion that created it happened about 6,500 years before those observers ever saw it, because the light took that long to cross the distance to Earth. So the sky is full of time layers. You look up and you do not just see far, you see then. And once you accept that, you start noticing the biggest structure you can observe from inside it, the Milky Way. On a dark night away from city lights, you can see it as a pale band stretching across the sky, like a river of faint white glow. That glow is not a cloud. It is the combined light of an absurd number of stars, most of them too faint and too crowded together for your eyes to separate individually. Ancient people saw that band and named it like they named everything else, by analogy. In Greek, the word galaxies means milky, which is where our word galaxy comes from, and where the Milky Way gets its name. For most of human history, that band was a mystery. People imagined it as divine milk, as smoke, as a road, as a crack in the sky. But it is something far more physical and far more intimidating. It is our home galaxy seen from the inside. The Milky Way is a barred spiral galaxy about 100,000 light-years across. Think about that as a travel time problem, not a picture. 100,000 years would be needed for light itself to go from one side to the other. If a beam of light started its journey across our galaxy at the moment the first humans began leaving Africa, it would only be arriving at the far edge right about now. That is the scale of the structure you're trapped inside, and it is crowded. The Milky Way contains somewhere between 100 billion and 400 billion stars, with many estimates landing around 200 to 300 billion. Counting them becomes a strange thought experiment. If you counted one star per second without stopping, you would be counting for thousands of years. Not because the stars are hard to see, because there are too many. Somewhere in that vast barred spiral we live in an ordinary suburb. Our solar system sits in one of the spiral arms, about 26,000 light-years from the galactic centre. We are in a region often called the Orion Arm, sometimes described as the Orion Spur, a smaller branch of the larger spiral structure. From here, when we look toward the centre, we are looking through thick lanes of interstellar dust, and that dust blocks visible light the way fog blocks a distant city skyline. The centre of our galaxy is bright and busy, but much of it is hidden from the kind of light your eyes evolved to use. That is why the Milky Way is such a strange place to study. We are inside it, so we cannot step outside for a clean photograph. We're trying to map a city while standing in one of its streets, surrounded by buildings, blinded by smoke, guessing the layout from echoes and glimpses. We use other kinds of light to see through the dust. We track the motion of stars. We listen to radio waves. We measure the pull of gravity. We build a picture from indirect clues. And when we do, one region of the map starts pulling all our attention like a dark magnet. Because near the very centre of the Milky Way, something is sitting there that does not shine like a star, but controls the movement of stars around it. Something that forced astronomers to accept that black holes are not just math, they are real. At the Milky Way's centre, there is no bright star to point at. There is no glowing beacon that tells you, here it is. What you find instead is a crowded, dusty region where visible light struggles to escape, and where the most important object is defined by what it does not let you see. For a long time, black holes lived in a strange category. They were a prediction from Einstein's theory of general relativity, elegant and disturbing. Many physicists accepted the math but hesitated at the reality. Maybe black holes were just an odd solution on paper. Maybe nature never actually made them. Maybe the universe had some hidden rule that prevented matter from collapsing that far. Then the Milky Way's centre started answering back. Astronomers realised the region was packed with stars, all moving as if they were orbiting something heavy that could not be seen. It was like watching leaves swirl around an invisible drain. You could not see the drain, but you could not deny the pattern. In 1974, scientists detected a powerful radio source near the galactic centre. It became one of the key signposts of this mystery, eventually associated with what we now call Sagittarius, a star. The name sounds gentle, almost like a catalogue entry, but the object it points to is anything but gentle. It is a supermassive black hole, with a mass millions of times greater than the Sun, sitting at the centre of our galaxy like a silent anchor. How do you prove something invisible is there? You do it the same way you prove a strong wind is there when you cannot see the air. You watch what it moves. Over the past few decades, astronomers tracked individual stars orbiting close to the galactic centre. These stars move fast, unbelievably fast, whipping around a point in space that looks empty. Some complete full orbits in just a few years. Their paths are not random. They are tight, curved and consistent, the signature of a massive object with a very small volume. The faster and tighter the orbit, the stronger the conclusion. Something compact and massive is there, and it is controlling everything nearby. This was not one observation. It was a long campaign of patience, night after night, year after year, watching tiny points of light drift and arc, letting time do the work of drawing their orbits in the sky. The galaxy itself became the lab notebook. In 2020, scientists Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for work that included measuring these stellar orbits and strengthening the case beyond reasonable doubt that a supermassive black hole sits at the centre of our galaxy. It was the kind of confirmation that feels almost anticlimactic, because the evidence had been piling up for so long. But it mattered. It turned the black hole from an idea into a measured fact. Still, there was one more thing people wanted. Not a proof through motion. A picture. In 2022, the Event Horizon Telescope collaboration released an image connected to Sagittarius A star. It was not a photograph in the ordinary sense. You cannot photograph a black hole directly because a black hole does not emit light. What you can image is the glowing material around it, gas heated to extreme temperatures as it spirals inward, accelerating, compressing and shining just before it disappears. The result was haunting. A bright ring of superheated gas surrounding a dark centre, a shadow where light should have been. That dark region is not the black hole itself in the way you might imagine a solid object. It is the silhouette made by gravity bending and trapping light, the visual fingerprint of the event horizon's presence. And this is where the concept becomes almost physical. A black hole is defined by its event horizon, a boundary in space beyond which nothing can return. Not matter, not messages, not light. Things can orbit outside it. Gas can swirl around it. Stars can pass nearby and survive. But once anything crosses that boundary, it is gone from our universe in the most practical sense. Not erased from existence, but erased from access. So Sagittarius A star is not just a monster in the middle of the Milky Way. It is a kind of limit, a place where the idea of escape fails. Now here is the unsettling part. Our supermassive black hole is relatively quiet compared to the blazing centers seen in some other galaxies. In those galaxies, black holes feed aggressively. They swallow large amounts of gas and dust, and the infalling material can power jets of energy that blast outward across enormous distances. Those jets can shape entire galaxies, carving paths through gas, heating regions of space, and leaving bright signatures visible from billions of light years away. Sagittarius. A star is not doing that right now, but evidence suggests it has not always been so calm. The galactic center shows signs that in the distant past, millions of years ago, our black hole may have been more active, swallowing more material, releasing more energy, leaving traces that still linger in the structure and radiation of the region. That contrast is eerie. The thing at the center of our home galaxy is quiet today, but it is not guaranteed to remain quiet forever. If enough gas falls inward, if a dense cloud drifts too close, if a star gets torn apart and fed into the drain, the center can flare, the monster can wake up. And while all of this is happening, we are not spectators standing still, we are part of the system. Our sun orbits the galactic center at about 500,000 miles per hour. That speed sounds outrageous, and it is by everyday standards. But in a galaxy 100,000 light years across, it is just the pace of a slow, long dance. At that speed, the sun takes on the order of 230 million years to complete one full orbit around the Milky Way center. 230 million years. When the sun was completing early laps around the galaxy, dinosaurs were only beginning to evolve on Earth. They rose, dominated the planet, went extinct, and mammals rose afterward, all within a handful of galactic orbits. Our sun has completed only about 20 orbits since it formed. The entire history of the solar system fits inside that small number, which means our sense of time is deeply local. We measure centuries and feel ancient. The galaxy measures hundreds of millions of years and barely notices, and now, with Sagittarius A star anchored in the center of our minds, the Milky Way becomes more than a beautiful band in the sky. It becomes a structure with a heart, a rotation, a history, and a future. A place shaped by gravity on every scale, from planets to stars to black holes that can rewrite everything around them. But even this huge home is not the whole story. The Milky Way is one galaxy among many, and the next step in our journey is the first time we truly leave home behind. We're going to step outside the Milky Way and aim for the nearest major galaxy, a spiral giant that is already on a slow approach toward us across the dark. There is a galaxy you can see with your naked eye, and most people never notice the weirdness of that fact. On a dark, clear night, far from city lights, you can look up and find a faint smudge in the sky. It does not sparkle like a star. It looks like a soft patch of fog, a quiet blur that seems almost accidental. That smudge is Andromeda, a galaxy so far away that the light reaching your eyes tonight began its journey before humans were writing down history the way we do now. Andromeda is about 2.5 million light years away. That number deserves a slow inhale. 2.5 million years. The light you see left Andromeda around the time our ancestors were living as early humans in a very different world. The Earth's climate was different. The landscape was different. The cast of animals was different. Everything about the human story was still young and fragile, and yet the galaxy was already there, spinning, forming stars, living its own giant life, while Earth was still figuring out what it wanted to become. This is the first time our journey changes from neighborhood travel to true intergalactic scale. Proxima Centauri was the first abyss between stars. Andromeda is the first abyss between galaxies. Now here is the part that feels like a plot twist. Andromeda is not just a distant object, it is a destination in motion. Astronomers have measured that Andromeda is moving toward the Milky Way. Not fast in the way a car moves, but fast in the way galaxies move, through the slow gravity-shaped flow of the universe. The two galaxies are on a collision course, and the expected timeline is roughly 4 billion years from now. 4 billion years is both absurdly far away and uncomfortably meaningful. It is close enough that the Sun will still exist. It is close enough that the Milky Way will still be the Milky Way in a recognizable sense. It is far enough that the Earth of today will not be there as we know it, because our planet's story is tied to the Sun's slow evolution, and the Sun will not stay the same. So the central question becomes a deliciously dramatic one. What does a galaxy collision actually look like? Most people imagine it like two solid objects crashing together, a sudden impact, a bright explosion, a cosmic car wreck. But that mental image is based on the way solid things behave on Earth. Galaxies are not solid, they are mostly empty space. Even within a galaxy packed with hundreds of billions of stars, the distances between stars are enormous. If the Sun were the size of a marble, the nearest star would still be miles away at that scale. So when galaxies collide, most stars do not hit other stars. They pass by, they drift through, they swing around each other like dancers in a slow, chaotic waltz. That is the counterintuitive turn that makes galaxy collisions feel eerie rather than violent. A galaxy collision is less like smashing two cars and more like merging two swarms of fireflies in a cathedral-sized void. But do not mistake that for harmless. While stars rarely collide directly, gravity reshapes everything. As the Milky Way and Andromeda approach, their mutual pull will distort their shapes. Spiral arms will stretch and warp. Streams of stars will be pulled into long arcs. Some stars will be flung outward into intergalactic space. Others will drop into new orbits closer to the combined center. And the really important action happens in the gas. Galaxies contain clouds of gas and dust, and those clouds are much more likely to interact than stars are. When gas clouds collide, they compress. When they compress, they can trigger bursts of star formation. In many galaxy collisions we observe in the universe today, you see bright regions where new stars are being born in intense waves, as if the collision squeezes the galaxies and forces them to light up with newborn suns. So the Milky Way Andromeda collision will likely create fireworks, not from stars smashing into each other, but from gas being shocked and stirred into new creation. It is destruction and birth tangled together, the universe doing what it always does, rearranging matter, recycling it, turning old structures into new ones. Now put yourself back inside the story, because this is not just a distant drama. We are inside one of the galaxies involved. We are not watching from a safe external seat. We are riding along on a small rock orbiting a medium star, orbiting a supermassive black hole inside a spiral arm that will eventually be tugged and twisted by a cosmic neighbour. So what happens to the solar system when this begins? The honest answer is that no one can predict the exact details for our particular star, because the dance is chaotic. Small differences early in the interaction can lead to different outcomes later, but the big picture is clearer. The Sun will almost certainly not collide with another star. Space is too empty for that to be likely. Instead, the Sun's orbit within the galaxy could change. We might be shifted to a different region of the combined galaxy. We could end up farther from the center, or closer, or in a long looping orbit that takes us through regions of different stellar density. The night sky from any surviving planet would become spectacular, because Andromeda would grow from a smudge to a sprawling presence, filling a large portion of the sky as the galaxies approach, then stretching into arcs and ribbons during the merge. If there are still observers then, they will witness a sky that looks like it is breaking and reforming in slow motion, a reminder that the cosmos is not static scenery. It moves, it evolves, it collides. Now zoom out one more step, because Andromeda and the Milky Way are not alone. They are part of a small collection of galaxies bound together by gravity, called the Local Group. This group includes our two big spirals, the Triangulum Galaxy, and dozens of smaller dwarf galaxies that orbit and interact over time. The Local Group is like a neighborhood cluster in the cosmic web, a few dozen galaxies sharing a gravitational region in an expanding universe. And that detail matters because it tells you something profound. On the larger scales, the universe is expanding, pulling distant galaxies away. But on local scales, gravity can hold structures together and even pull them into mergers. Expansion and gravity are both true at once, operating on different scales like two overlapping laws of motion. So the Milky Way-Andromeda collision is not an exception to expansion. It is a reminder that the universe is more subtle than a simple image of everything flying apart. Some things are fleeing, some things are falling together, and when the Milky Way and Andromeda finally merge, the likely result is a new kind of galaxy. Two spirals merging can form a larger, more rounded galaxy, often described as elliptical in overall shape. The combined system will have a new structure, a new distribution of stars, and eventually a new central black hole story, as the two galactic centers settle into one. That last point is the one that makes the tension sharpen again. Because both galaxies have supermassive black holes at their centers. In the far future, those black holes will likely spiral toward each other and merge, releasing ripples in space-time, gravitational waves that travel outward across the universe. A galaxy collision ends with a black hole union. That is the kind of ending the universe writes when it has billions of years to build suspense, and this is why Andromeda matters in our story. It is the first object that forces you to accept that galaxies are not distant, isolated islands. They are part of a living ecosystem that interacts, merges, and reshapes itself over time. But there is an even larger structure beyond the Local Group, and once we step into that, the scale will jump again. We're going to leave the comfort of two galaxies and enter the realm of clusters, superclusters, and the cosmic web, where galaxies behave like neurons in an enormous dark network. Once you leave the Local Group behind, the universe stops looking like a scattering of lonely islands and starts looking like a city at night. Not streetlights placed randomly, but neighborhoods, districts, downtown cores, and highways of motion that you can sense even when you cannot see the whole map at once. Galaxies gather, gravity makes sure of it. Stars gather into galaxies, and galaxies gather into groups, and groups gather into clusters. These clusters can contain hundreds or thousands of galaxies bound together, each one a spinning city of stars, all of them caught in a shared gravitational embrace. The nearest major example is the Virgo cluster. It sits about 54 million light-years away and contains more than 2,000 galaxies. That distance is already a psychological cliff. 54 million years is older than humanity by an absurd margin. When the light now reaching your eyes from the Virgo cluster began its journey, Earth was a different world. And the Virgo cluster is not floating alone. It is the core of a larger structure often described as the Virgo supercluster, a region of galaxy groups and clusters stretching across roughly 110 million light-years. A supercluster is not a single neat object with a clean boundary. It is more like a region where matter is denser than average, where gravity has persuaded galaxies to drift in similar directions, where cosmic traffic has patterns. Inside the Virgo cluster sits one of the most famous galaxies on the deep map, Messier 87. It is one of the most massive galaxies known, containing several trillion stars. At its centre is a supermassive black hole weighing about 6.5 billion times the mass of the Sun. Long before the first image of Sagittarius, a star, it was this monster in Messier 87 that gave us a historic first glimpse of a black hole's shadow, a glowing ring of heated gas wrapped around darkness, a place where escape fails. So already the scale has shifted again. We're no longer talking about planets around a star or stars in a galaxy. We're talking about galaxies gathering into greater ecosystems and black holes that act like anchors in the hearts of giant stellar cities. Now comes the part that feels almost personal because it involves us. Our local group is not simply drifting in quiet isolation. Our whole neighbourhood is moving in a larger flow. We are falling toward the Virgo cluster at about 250 meters per second, which is roughly 560 miles per hour. That does not mean we're headed there like a spaceship with a destination. It means gravity is pulling on the entire region, and the motion is measurable. The cosmos has currents, and we are inside one of them. But even this is not the whole map. When astronomers traced these motions farther out, the Virgo supercluster became a chapter inside an even larger story. Our galaxy sits in the outer reaches of a vast structure called Laniakea, which translates to immense heaven in Hawaiian. Laniakea was identified in 2014 as a structure containing about 100,000 galaxies spread across 520 million light-years. That is not a cluster you can point to with a clean circle. It is a basin of attraction, a region where countless galaxies share a general drift, like water flowing down a shallow continental slope. When researchers mapped the motions of galaxies throughout our region, they found that much of this flow seems to head toward a mysterious gravitational region often called the Great Attractor. The Great Attractor is not a single known object you can photograph easily. We cannot see it directly because the Milky Way's disk blocks our view in that direction. But we can detect its influence by watching how galaxies move, how their paths bend, how their velocities line up like iron filings around an unseen magnet. This is the moment the universe starts feeling less like a static picture and more like a living process. Things are not placed, they are moving, they are falling, they are flowing. And then the map widens again, and you discover that even Laniakea is not the end of the hierarchy. On the very largest scales, the universe looks almost like a cosmic sponge. Matter is concentrated into thin walls and filaments, and those filaments surround mostly empty bubbles. Galaxies are not sprinkled evenly everywhere. They trace out a web, long strands of structure that meet at dense knots where clusters live, while huge regions between those strands can be eerily empty. Some of the biggest named structures we know sit on these threads. One of the most famous is the Hercules Corona Borealis Great Wall, discovered in 2013 and described as one of the largest known structures in the universe. The scale is so extreme that when you talk about light crossing it, you're not talking about human history. You're talking about eras so deep that when the light now reaching us began that journey, our sun and earth did not even exist yet. And where the web is thinnest, you find voids. Cosmic voids are regions of space often hundreds of millions of light years across that contain almost no galaxies at all. They are not perfectly empty. There can be a few lonely galaxies inside, but far fewer than you would expect if matter were evenly spread. One famous example is the Bootes Void, discovered in 1981. It is about 330 million light-years in diameter and contains far fewer galaxies than would be expected for a region that size. That emptiness is not just a fun fact, it is a clue. The existence of voids and filaments tells us something about how the universe grew its structure. In the early universe, matter was not distributed perfectly evenly. There were tiny differences in density. Places that were slightly denser pulled in more matter over time, and places that were slightly less dense lost matter to their denser neighbours. Gravity turned faint unevenness into dramatic architecture. Over cosmic time, those small beginnings became the filaments, clusters, and voids we see today, like a fossil imprint of the universe's earliest texture. So now take a breath and absorb the shift. We started with Earth, then the Moon, then the Sun, then the outer planets, then the nearest star, then the Milky Way, then Andromeda. Now we are looking at a universe where galaxies form networks, where whole regions flow toward unseen mass, where the largest structures are walls and threads, and where emptiness can span hundreds of millions of light years. It is tempting to think we have reached the top of the scale ladder, the biggest things, the final map. But there is one more twist, and it changes what distance even means. Because all of this structure, all of this webbing and flowing and clustering, is happening inside a universe that is not standing still. The cosmic web feels like the biggest map there is. Filaments, clusters, walls, voids, a universe that grew patterns the way frost grows on glass. But here's the twist. That entire map is drawn on fabric that refuses to sit still. The universe is not a fixed stage where galaxies perform. The stage itself is stretching while the play is running. In 1929, astronomer Edwin Hubble noticed something that changed everything. When he looked at distant galaxies, their light was shifted toward the red end of the spectrum. The farther away a galaxy was, the stronger that shift tended to be. This pattern told us the universe was expanding. Not in the simple sense that galaxies are blasting through space like shrapnel from an explosion, but in a stranger sense that takes a moment to swallow. Space itself is expanding, and galaxies are largely being carried along with it. A good way to feel this is to imagine raisins in rising dough. The raisins do not need to crawl away from each other. The dough expands between them, and the distance grows. From the point of view of any raisin, every other raisin seems to be moving away. The farther one appears to be, the faster its distance increases, simply because there is more dough in between expanding. That idea is the key to one of the most famous cosmic paradoxes. The universe, as we understand it, began about 13.8 billion years ago. So a common instinct is to say this: if nothing can move faster than light, then the farthest we could possibly see should be 13.8 billion light years away. Light has only had 13.8 billion years to travel, so how could we observe anything farther than that? And yet, when astronomers talk about the observable universe, they give a number that sounds like it should be impossible. The observable universe is about 93 billion light years across. How can both of those statements be true? The answer is that while light was travelling, the space it travelled through was stretching. Imagine you throw a ball across a rubber sheet. The ball leaves your hand and travels in a straight path toward the other side, but while it is in flight, someone stretches the rubber sheet, making the distance longer. The ball does not need to suddenly speed up. It simply arrives at a place that is now farther away than it was when the ball began its trip. Light from the early universe did the same thing. It started out when everything was closer together. Then, as it travelled, space expanded, pulling regions apart, increasing the distances between them. So when that ancient light finally reaches us, the source region is no longer at the simple light travel distance you would expect. It is much farther away today because the universe expanded the whole time. This is why you will sometimes hear another number paired with the 93 billion. The edge of what we can observe in any direction is about 46 billion light years away today. Double that for the full diameter, and you get the roughly 93 billion light-year width of our observable bubble. Now we need to be careful with language here, because words like edge can trick you again. The edge of the observable universe is not a wall. It is not a border you could fly to and bounce off. It is a horizon. It is the limit of what light has had time to reach us since the beginning. Beyond that horizon, there may be more universe. There may be an endless amount. It might even be infinite for all we know. But whatever lies beyond has not had time to send us information, so for us, it is effectively hidden, and the expansion itself has another mind-bending consequence. Some very distant galaxies are receding from us so fast that light emitted from them today will never reach us in the far future. That can sound like it breaks the rule that nothing can travel faster than light. But the rule applies to motion through space. The expansion is the stretching of space. Space can expand in a way that increases the distance between two places faster than light could cross that growing gap. So our observable universe is a temporary privilege. It is what we can see right now, given the age of the universe and the history of expansion up to this moment. And when you finally let that settle, the 93 billion light-year number stops being a fun trivia fact and starts becoming a kind of existential pressure. Because inside that bubble is an almost absurd amount of stuff. Within the observable universe, there are on the order of 2 trillion galaxies. Each galaxy can contain billions or hundreds of billions of stars, and some contain far more. The total number of stars is so large that ordinary comparisons start to fail. People reach for images like grains of sand on all Earth's beaches, not because that is a perfect measurement, but because it is one of the few things your mind recognizes as overwhelmingly many. And around those stars are planets. We now know that planets are common. Many stars have multiple planets. Some have systems that look nothing like ours. When you combine that with the sheer number of stars, you end up with a staggering number of potential worlds, far beyond what any human lifetime can truly picture. This is the emotional turn in the expansion story. The universe is not just big in space, it is big in time, and it is changing while we try to understand it. The horizon of what we can observe is not just a distance, it is a deadline written by physics, which raises the next tension in our journey. If expansion shapes what we can see, what is driving that expansion, and why does it appear to be speeding up? The edge of the observable universe is not a fence, it is not a wall, it is not a place you could travel to and plant a flag. It is a horizon made of time, a limit set by one simple fact. Light has only had so long to reach us since the beginning, and beyond that limit the universe has not had enough time to tell us what is there. That horizon is already strange enough, but then we notice something even stranger. The expansion of the universe is not slowing down the way many scientists once expected. It is speeding up. Something is pushing space to stretch faster and faster, as if the universe has a hidden accelerator pedal. We call the driver dark energy, not because we understand it, but because we do not. The name is a label for ignorance with a serious face. We can measure its effect through how the universe expands, but we still do not know what dark energy actually is. This is where the future starts to get eerie. If expansion keeps accelerating, more and more galaxies will drift beyond our horizon. Not because they vanish, but because their light will no longer be able to catch up to us. Imagine a boat rowing upstream while the river speeds up under it. The boat can row perfectly, but if the current grows strong enough, it will never reach you. In the far future, a civilization could look up and see far fewer galaxies than we see today. Eventually, they might see almost none beyond their local neighborhood. They would not know the universe is vast, not because the universe got smaller, but because the evidence would have slipped away beyond a horizon they cannot cross. Even the cosmic microwave background, the afterglow of the early universe, would fade from view in a deep way. As space continues expanding, that ancient light gets stretched to longer and longer wavelengths. Over enough time, it can become so diluted and so shifted that it is effectively undetectable. Future observers could be trapped inside a cosmic illusion, surrounded by darkness and convinced the universe is mostly empty, because the oldest and biggest clues have moved out of reach. So the horizon is not just the edge of sight, it is the edge of evidence. Now add one more layer of weirdness, because cosmology loves stacking strange on strange. There is an idea called inflation. The basic claim is that in the earliest instance after the universe began, space may have expanded extremely rapidly, far faster than the slower expansion we see today. Inflation is not a decorative theory. It was proposed to explain why the observable universe looks so uniform in temperature in every direction. and why space appears so flat on large scales. Some versions of inflation lead to an even wilder possibility: eternal inflation. In that picture, inflation does not end everywhere at once. Instead, it ends in patches. Each patch becomes a universe like ours, while other regions keep inflating, producing more patches again and again. If that is true, then our observable universe is not the whole universe. It is one bubble in a much larger foam, possibly containing many other bubbles that we can never reach or communicate with. People call this the multiverse. This is where we need intellectual discipline. The multiverse idea is highly speculative. It is not confirmed the way galaxy expansion is confirmed. It is a working possibility that grows out of certain models. It might be right, it might be wrong. But even the fact that serious scientists discuss it is a sign of how strange the universe has forced our theories to become. And now we arrive at the emotional knot in the middle of all this. If the universe is that big, even just within our observable bubble, it becomes hard to believe we're alone. We're looking at on the order of 2 trillion galaxies. Each of those galaxies can hold billions or hundreds of billions of stars. Planets appear to be common. Chemistry is common. Time is abundant. So a natural question rises like a pressure you cannot ignore. Where is everybody? Physicist Enrico Fermi famously asked a version of that question in a lunch conversation in 1950. The logic is simple and brutal. If life and intelligence are common, and if the universe is old, then evidence should be everywhere. Signals, artifacts, engineering footprints, something. But we do not see it. We hear no obvious broadcast from distant worlds. We do not find clear signs of alien technology written across the sky. We face a kind of emptiness that feels suspicious, like walking into a city and hearing no voices. This is sometimes called the Great Silence. Part of the silence might be pure physics. Our own radio signals have only been leaking into space for about a century. That means our loudest bubble of electromagnetic noise is only about 100 light-years wide. That is a tiny fraction of our galaxy, and our galaxy is already just one island in a much larger sea. Even worse, those signals spread out. They get weaker as they travel. By the time they reach a distant star, they may be nearly impossible to pick out from the background hiss of space. Even if another civilization is listening, they would have to be listening in the right way, at the right time, with the right sensitivity, pointed at the right region of sky. There is no guarantee any of those conditions line up. And even if we did detect a signal, the conversation would be slow. A civilization 50 light-years away would receive our message 50 years after we send it. Their reply would take another 50 years to return. This is not a problem you solve with better engineering. It is a law of reality. Nothing carries information faster than light. So the Great Silence might be an illusion created by distance, weakness, and time lag. But the silence could also mean something heavier. Maybe intelligent life is rare. Maybe the jump from simple single-celled life to complex multicellular life is an unlikely step. On Earth, life existed for billions of years before complex animals appeared. Maybe that transition is the real bottleneck, the hard gate most worlds never pass. Maybe intelligent life is fragile. Civilizations might not last long on cosmic timescales. They could destroy themselves through war, ecological collapse, or accidents from powerful technologies they do not fully control. A technological species might burn bright and then vanish quickly, leaving a galaxy that is mostly quiet most of the time. Maybe we are early. The universe needed time to make heavier elements, time to build rocky planets, time to let chemistry run long enough for complexity to emerge. Perhaps we are among the first civilizations to appear, living at the beginning of an era that will later be crowded. Or maybe the truth is even stranger than our categories. Maybe advanced civilizations do not broadcast. Maybe they hide. Maybe they communicate in ways we're not looking for. Maybe our assumptions about what evidence should look like are shaped by a species that has been technological for only a blink. None of these possibilities are comfortable. That is what makes them useful. Because when you put expansion, horizons, dark energy, and the great silence together, you get a sobering picture. The universe may be full of life and still feel silent. It may be vast and still become lonely for future observers. It may contain endless regions beyond our reach, and we might never know. And yet, here we are, in this brief window where the sky's rich with galaxies, where the cosmic microwave background still whispers, where we can still map the web, still ask the big questions, still chase answers before the horizon steals them. In the final part, we take the long view to its end. We follow the universe forward in time, from the future of the sun, to the collision of galaxies, to the fading of the sky itself, and we ask the only question that really matters when you finally understand the scale. What do we do with our short moment of awareness? When you look at the universe on human timescales, it feels stable. The sun rises, the moon cycles, the stars hold their positions like the sky is a permanent ceiling. But the universe is not stable. It only looks stable because our lives are short. Time is doing its work anyway, slow and unstoppable, reshaping everything we have talked about, including the one world you have ever actually touched. So let's follow the story forward. The sun is not a fixed engine. It is a star in midlife, and it changes as it burns fuel. Over time, the sun gradually gets brighter. Roughly speaking, its brightness increases by about 1% every 100 million years. That sounds gentle, like a change you could ignore. But give it enough time and gentle becomes decisive. A brighter sun means a warmer Earth. A warmer Earth means oceans evaporate faster. Water vapor is a greenhouse gas, which means more heat gets trapped, which means even more water evaporates. It is a feedback loop, and feedback loops are how nature turns slow nudges into irreversible turns. Long before the sun actually dies, Earth's surface could become hostile to complex life. Our planet's habitable era is not forever. It has a clock built into the physics of stars. Then, in roughly 5 billion years, the sun will begin its dramatic transformation. As its core runs low on hydrogen, it will start fusing hydrogen in a shell around the core, and the outer layers will expand. The sun will swell into a red giant, growing to around 200 times its current size. In that swollen phase, it is expected to engulf Mercury and Venus. Earth's fate is complicated. Some models suggest Earth could be engulfed as well. Others suggest Earth could survive but be scorched and stripped, a burned rock in a widened orbit. Either way, the Earth you know does not make it through that era. Eventually the sun will shed its outer layers, leaving behind a white dwarf, a hot, dense ember roughly the size of Earth, cooling slowly over trillions of years. The familiar solar system will become a colder, quieter place, a set of survivors orbiting a fading remnant. While that is happening, the galaxy story continues. In roughly 4 billion years, Andromeda and the Milky Way will begin their long merge. The night sky will change in ways we can barely imagine. Andromeda will grow larger and brighter, stretching across the sky as the distance closes. Over time, the two galaxies will distort each other. Star streams will arc like luminous rivers, and new waves of star formation could ignite as gas clouds compress and collide. Eventually, the two galaxies will settle into a single larger system, likely a more rounded, less clearly spiral galaxy. The Sun, if it still exists in any meaningful way as a star at that point, will be carried into a new orbit within the merged galaxy. We might end up in a different region of the combined system, with a different view of the galactic center, a different night sky, a different neighborhood of nearby stars. And deep in the center, another slow climax unfolds. Both galaxies have supermassive black holes. Over time, those black holes will spiral toward each other and merge. When they do, they will release gravitational waves, ripples in space-time that travel outward at the speed of light. The universe will literally ring like a struck bell, not with sound, but with geometry. Even that is not the end of the long timeline, it is just a chapter. If dark energy continues to drive accelerated expansion, the far future will become quieter and lonelier from the perspective of any given galaxy group. More galaxies will slip beyond the cosmic horizon. The universe will not suddenly go dark everywhere, but your accessible universe will shrink. The sky will empty. Distant galaxies will become too far for their light to ever reach you again. In that far future, observers in a galaxy like ours could see only their local merged system, and perhaps a few nearby dwarf galaxies still gravitationally bound. Everything else would fade beyond reach. The cosmic web would become unobservable. The story of the Big Bang could become difficult to infer. The universe would still be enormous, but it would look small. Then comes the long fade of stars. Star formation depends on gas, and gas gets used up. Over immense time, galaxies turn their gas into stars, and much of the remaining gas can be heated, expelled, or locked into forms that do not easily collapse into new suns. The cosmic era of starbirth does not last forever. Eventually, the last red dwarfs will burn out. This is hard to emotionally picture because it happens on timescales so huge they barely fit inside language. Red dwarfs can shine for trillions of years. That is thousands of billions of years. That is longer than the current age of the universe by a factor of hundreds. But even red dwarfs do not live forever. After the last stars fade, the universe enters an era dominated by stellar remnants. White dwarfs cooling, neutron stars cooling, black holes silently orbiting through darkness. The universe becomes a colder place, not because a thermostat was turned down, but because the engines that created light have gradually shut off. Even black holes are not eternal, at least in our current understanding. Through a process called Hawking radiation, black holes can slowly lose mass over extremely long timescales, eventually evaporating. For stellar mass black holes, the timescale is unimaginably huge. For supermassive black holes, it is even longer. But the key idea is simple. Even the darkest objects may have an ending. And at the far edge of speculation, beyond the last light, beyond the last structures, beyond everything that looks like a story, you are left with a universe that is cold, thin, and quiet. So why talk about any of this? Why spend time stretching your brain across scales you can never travel, times you will never witness, and distances that turn you into a temporary flicker? Because the scale does not make you meaningless. It makes you rare in a different way. You are matter that learned to notice itself. You are stardust that learned to ask where it came from. The atoms in your body were forged in stars that lived and died long before Earth existed. The oxygen you breathe, the iron in your blood, the calcium in your bones, these were built in cosmic furnaces scattered by explosions, mixed into clouds, and eventually assembled into a planet that produced minds capable of wonder. And wonder is not just a feeling, it is a tool. When you look up and realize how big the universe is, it becomes harder to pretend that petty hatred is profound. It becomes harder to treat other humans as if they are not part of the same fragile experiment. It becomes harder to waste the only known pocket of life we have ever found. The universe is enormous, but our window is small. Our planet is temporary. Our star is mortal. Our galaxy is moving. Our observable horizon will change. The sky itself has a future. That could make you nihilistic, or it could make you awake. Because right now, in this thin slice of cosmic history, we can still see the deep universe. We can still map clusters and filaments. We can still detect faint afterglows from the beginning. We can still build instruments that read the universe like a book written in light. And you are alive at the moment when the book is still open. So take that seriously in the most human way. Learn, explore, be curious, be kinder than you have to be, make things. Protect the fragile world that lets you ask these questions in the first place. The universe will not remember us, but we can remember the universe. and that is already something unbelievably strange and beautiful.